Awesome, 12 o'clock. Well, hello and welcome to the third of 5 sessions in our Knowledge Zone offering for 2024. As we wait for people to keep arriving, let me tell you about the tagline of a book I started reading just yesterday called Atomic Habits by James Clear. The tagline on the cover page is "Tiny Changes, Remarkable Results." Well, that's about all of the book I've read so far, but the tiny changes, remarkable results is the point in us running the seminar. It's about understanding impact on what you are designing or building and the need to apply new knowledge, especially as energy demands, earthquake performance requirements change. So we can't keep repeating what we've always done. That would be dumb. Today, we're pointing out some tiny changes in design or application that will have remarkable results for building performance outcomes. I wanted to encourage those of you who are interested in coming to the in-person event on the 13th of June to register. A reminder, it really does coincide with Pink Floyd, Armageddon and Bonsai weekends, so something for everyone. That in-person event is our live webinar, which is also live streamed. So the registrations are separate on our website, so check which one you're booked for. The stream will finish, and for those in Auckland with us, we will make available a hands-on experience with installing product on our training walls. We'll have a decent feed and then the professionally hosted quiz night. So let's get started on today's topic, E2, external moisture, and a continued discussion on how then should we build. What we know is through decades of trial and error, is that we should have somewhat of a dry suit around the building envelope with an umbrella over the top to reduce the water pressure on the dry suit. So that reference, umbrella or dry suit, it's both. And to help us unpack this concept and provide some simple solutions, we have Soren Webb presenting today, who I'll introduce in just a moment. The last sessions, we've looked at some minor structural element changes that can make a demonstrable difference to the thermal performance of a construction. We looked at design choices that dictate durability, rather than just treating timber. And following today's session, we have energy efficiency, H1, and then we finish up with what we've called the naughty child, E3, internal moisture. That's the online and in-person event. Right, during this presentation, we welcome your questions, your comments and objections. Where possible, we will answer those along the way. Most of them, though, we will leave to the end. Please find the chat function on your screen. In the chat box, we will post some links to you during the presentation alongside the QR codes that you'll see on the screen. If you have a question, please use the question tab and then they will be collated and we'll try and get to all of those. NZRAB, CPD points, 10 points for this presentation. We load that for you, 1 LVP point you claim for yourself through the portal. During the presentation, we have a few poll questions that will be answered by 2 of our nationwide team. So we have Richard Hollard, based in Auckland, and Ben Ingledew, who is based in Christchurch. We'll bring them in to briefly discuss poll questions and they will be available at the end for our Q&A. Well, Soren is our regional sales manager based in Wellington and covering a little triangle between Wellington, New Plymouth and Napier. That's actually quite a distance, so thankfully he's a totally self-confessed petrolhead, loves driving, any excuse to go off-road in his four-wheel drive. Soren studied at Victoria University in Wellington under New Zealand's best, such as Mike Don. He holds a Bachelor of Building Science, which at the time, a long time ago, was a combination of architecture and building science. So that sounds good. And on that note, I'm going to hand over to you, Soren, to unpick a bit of E2 for us. Over to you.
Thank you, John. Today, we're going to talk about external moisture. And once we're done, you'll all be implementing on your next projects the simple concept of continuous weather resistive barrier. Previously, my colleague Richard Hollard spoke about durability and the consequences of getting it wrong. Without taking care of E2, you won't achieve B2 durability, which then undermines B1 structure, which was Simon Cater's topic. Recordings of these presentations will be available by request if you have missed any of them. you can see why E2 is so important, but why are we getting it wrong? Peter Dyer wrote a book on New Zealand's leaky building disaster called Rottonomics. This is what that book looks like. And you can see the QR code in the slide there for a link to his YouTube video on that. We won't have time today to go over every E2 detail. However, we will discuss the ethos you can apply. Here's a wall cutaway showing cladding cavity construction. This presentation is going to move around a few elements of the external envelope and discuss the 4 Ds, which are deflection, drainage, drying, and durability. So let's go through them one by one. Deflection. We've got 2 layers of defense, the cladding line and the weather resistive barrier. Drainage. We're draining down the outer face of the cladding, down the inner face of the cladding, and down the weather resistive barrier. Drying. We're allowing for air movement within the cavity. And durability. We're using exterior treated timber and durable materials for cavity construction. This lovely detail comes from a brand's science publication, and again there's a link to that in the QR code.
All right, thanks, Soren. So we just wanted to drop a poll question in quite early, or very early on into the presentation, because we need to be on the same page with what we're trying to achieve here. So let's get that poll question up, and so here is your opportunity to participate in this presentation. So what are we actually talking about with E2? So you'll note that it doesn't say E2 AS1, it's E2. This is the code clause E2, which we're referring to today. So what does E2 actually require us to do, specifically E2.2, if you've got the time to very, very quickly research this, but what are we required to do? Is it to keep water out? Is it to keep water away? Is it to prevent accumulation, or is it to prevent any moisture moving? So as you make your selection on that, I know our guys are already back on screen ready to discuss this point. How are we doing on that? So let's have a look. Great. Okay. Very interesting. Richard, take it away. What's our worst? What's our least one there? 3%. Why don't we start with that one?
The moisture moving. That's interesting. That's if it gets in, it can't get out. That's sort of what that's telling me. But or stop it getting in. I mean, do we want to say what the real answer is? The actual answer is already, or so we can talk about it.
It's interesting that people there just have said to prevent water getting in, and that's really the conception of that. And I think it's worth discussing why we think that. But yeah, what's the answer, John?
Do I need to answer that? Okay. Well, so we've still got we've got the keep water out was the 57% answer, but it's actually not true. So if we maybe put a whole lot more words around that answer and said prevent water or keep water out of the structural frame, that might be true. But actually E2.2 says prevent accumulation of external moisture. And so Ben, question for you around that then is, what is that difference, and why is that fundamentally well, something that we should understand from a fundamental perspective when we're designing?
The problem comes with the accumulation that if water will get in, it's very, very difficult to keep water out. You can't develop a cladding system that is watertight. We're not building submarines here. What we're building is houses, and just like in a multi-story high-rise where we've got a glass facade, or in a residential system with cedar cladding, it's the water will get behind it, but the real question is being able to get that drained away, and that's the drainage, and then also to get it to drying, so the ventilation. That's the key.
Yeah, I was going to say if it was keeping water out, then it would only be probably the 2 Ds. It would be deflection and durability. But yeah, the fact that we've got drainage and drying capability or potential in our wall systems means that, hey, it does get in, recognises that it does get in, but it needs to get out as well. And if we look at, we've talked about woofy in previous webinars, and that, you know, you can see, you can model, you can see moisture and heat flowing in and out of the building all the time. It's a matter of less coming in than going out, you know, more drying than wetting capability. So recognising that, so stopping it building up as such. Yeah.
All right, so in that woofy, yeah, you're talking about the woofy simulation where you see the arrows pointing which way moisture is actually flowing through every material in an assembly. So the idea there is that the accumulation, we're trying to prevent accumulation of external moisture. It's about when it gets in, drying, draining that moisture back out. Great.
Yep.
All right, I think we should probably.
Sorry, just about some moisture loading. It's that moisture loading that is talked about in woofy, where you've got drying times and loading times. It's making sure that they're definitely in favour of drying.
Right. Right. I think we should jump back to Soren. That was a fairly lengthy answer, but Soren, back to you.
Nice, guys. That's spot on. So flexible wall underlays are intended to be used with rigid interior linings, which act as a baffle to stop it billowing in and out with fluctuations in external pressure. For example, where you have an attached garage with no internal linings, a rigid air barrier is required. With this in mind, it's prudent to use a flexible underlay. Is it prudent to use a flexible underlay for early closing? Probably not. The nicest solution is to use a rigid substrate with adhesive underlay over. And we've got in the QR code brand's opinion on early closing as well. In a sea spray zone, your proprietary rigid air barrier fixings will be stainless steel for durability. Consider the benefits if you utilize an adhesive backed weather resistive barrier over an acceptable solution rigid substrate, so the fixings are enclosed by the membrane. I think you'll find your savings from not needing stainless steel fixings offset the cost of the adhesive underlay. Here we have a plan view of a residence. The red line indicates the thermal envelope. The blue line is the weather resistive barrier. We routinely miss the need for wind tightness on internal walls to the garage. We should be using an external door for that door between the garage there and you can see the laundry bathroom area. For wind tightness, remembering continuity is key. Moving now to the base of the wall, we need a continuous weather and wind tight connection of the weather resistive barrier to the floor down past the bottom plate. This is super easy for you to implement. If you have a bottom plate offset by 6 mil, say, for the floor, from the floor to serve as a capillary break or construction tolerance, because that'll run in and out relative to your slab edge. How will that be wind tight? And what about maintenance water? Remember, the bottom plate on DPC, on floor, is surface upon surface, which is a big capillary moisture ingress risk. For rigid air barrier, seal the gap with facade sealant or fire-rated mastic, as the case may be. You can tape this, but the unders and overs won't be right. However, if you're using, again, the adhesive underlay over the rigid substrate, this will come down nicely over that tape. Or you can simply glue the underlay back to the slab edge or slab edge insulation. You're definitely going to be thinking about this a bit more next time you wash this part of your house. Allowing air in and out of the cavity is important for drying and allows the cavity pressures to quickly equalize and balance with external pressures. In order to achieve this, weather resistive barrier must be taped and continuous. Think about this. Table 23 requires the underlay to be a barrier to airflow, but the acceptable solution does not specify tape laps. So how does this work? The relatively recent 2020 EM7 evaluation method, however, combines air leakage testing of the weather resistive barrier with seismic lateral displacement and cycling water and spray at various pressures. So air tightness is key. This wall to Safite junction details from E2 AS1, and as you can see, the cavity is completely closed. There is a determination from 2013, number 046, that's titled Code Compliance of Top Ventilated Cavities of 2 Gisborne School Buildings. This can be used as detail guidance and a compliance path for top ventilation. There is a link to that in the QR code. And of course, MB guidelines now require top ventilation as well. Most cavity closers are manufactured to meet the building code requirement of 1000 millimeters square per lineal meter. This is for drainage and vermin protection only. This equates to a percentage open area of 5% for a 20 mil wide cavity. That's simply not going to allow enough drying airflow through the wall cavity, even when you create an open pathway out again at the head of the wall via top ventilation. Here is a 41% open area version that allows much better airflow. That's the one in black, powder coat, which is just a perforated aluminium sheet bent to dimension. The mill finish one on the right there, that's not a jib corner, it's a cavity closer in aluminium with similar high percentage open area. Talk to us about these if you have trouble finding them. Here is a typical E2 parapet detail. What can we do here? Let's first of all increase the height of the angle block above the top plate to ensure the cavity is continuous at this risk area. And let's illustrate this with a single line across it rather than the double cross there. And we'll call it out for clarity as well as discontinuous blocking at say 600 centers. It's very easy for a contractor to misinterpret this and end up solid blocking that, effectively going direct fix at this risk area. So you no longer have the benefits of the 4Ds. Let's also add a sill tape over the top plate. So the fixings for the blocking and the ply are sealed where they penetrate the horizontal surface of the weather resistive barrier. We'll take care to select a sill tape that provides one layer horizontal surface sealability, and we'll make the extent of this 50 mil down each wall face. And that's going to handle the penetrations coming all the way from the outside for the flashing fixings as well. Consider the maintenance man. He's going to come along with his ladder and prop it on the side of this. Would it be better to have the plywood extend over the cladding to stop the cladding getting loaded up by that or damaged, and also to support the outer edges of that flashing? What else can we do? What about top ventilating here at this location as well? So now we're going to another poll question.
Great. Thanks, Soren. Hey, just before we get that poll question up and going, I just want to cover, you've just had 4 pretty substantial pieces of advice. Firstly, it was the continuation, effectively an additional layer of wind-tight defense in the back of the garage wall, connected into the doorway, which is between garage and house. So that's by far and away one of the weakest doors in the building. It's often that very, very drafty door. So let's change that out. And yes, there's a cost there, but there's a massive improvement. So small change in the specification on that build and a big improvement in the actual performance. The second one there was looking at the base of wall. I know that we're going to have some questions around that, like you can't seal that off, you can't, well, we'll get to that in the discussion, but that is such a simple, and it's the same as what is happening at the back of the garage. If you stop drafts through underneath the door, if you stop drafts through underneath your wall underlay or rigid air barrier, then we've got an improvement in the wind type performance of the build, and therefore the overall performance of the build for comfort, for energy consumption. That is such a simple fix. The third one that you hit was the head of the wall, so head of the cladding and opening that up. So that's an improvement, and based on some really good science, first of all, around why you'd want to do that, to increase or to actually create a drying capacity up that wall behind the cladding. And then it's actually in the design guidance through the MOE for school buildings. So there must be some good evidence in that as well, that isn't just coming from us as a good idea. And then finally there, you talked about parapets. There's obviously a huge amount more that you could talk about around the parapets. So I'm just going to make it open season on you for the people who are listening in. If you want some more design advice or a bit more clarity around some of those things around the parapets, then please talk to Soren. So on that note, let's jump into the poll. And that poll question is, why would you continue? Now, I think we've actually got this one out of order, but we are going to do it anyway. Yep, this is out of order. This was supposed to come in after our discussion on Windows, but let's just do it. Why would you continue to design with E2 AS1 window details? So we are going to take a bit of a swipe at the E2 AS1 window details. We're going to look at why and what does work, and then why and what doesn't work. So what do you do right now? Let's start it there. What do you do right now? If you continue to, or if you do design with E2 AS1 window details, why do you do it? Answers are, it's accepted, it's acceptable, it's accepted without question by councils everywhere. That's why I choose it. You might be questioning now whether there was a problem at all. So, and then hopefully there'll be a few who never have designed with E2 AS1 window details, and they never will. So 4 answers there. Fill in your answers, and when we've got a fair portion of those, let's flick back to our panelists.
It's like a pre-test, John. That's what you've done there.
That's it.
You've done a pre-test.
So, all right.
That's what you meant to do, wasn't it?
Yes. Okay. I thought it worked okay. I'm going to start with 6%. So I thought it worked okay. Yeah, and I'm just going to point out that we are going to look at what does work, and there are elements for E2 where E2 AS1 window details do work. So Richard, Ben, up to you guys.
Interesting. I think there's obviously, it's the easy way out. Just design as per E2 AS1, and council's going to give it the tick, and you're going to build it quicker and without any hold-ups and RFIs. But E2 AS1 acceptable solution. It is just one solution of how to do stuff. It's not, doesn't mean it's the perfect way or the right way or the only way. There's if you can show with descriptions and good design how it complies with preventing accumulation of water, as we see that what the code is wanting us to do, what the clause is wanting us to do, then there's no reason why they can't accept that detail as a acceptable alternative.
And the E2 AS1 is, like you say, one solution. It is alternative solution, acceptable solution, acceptable solution 1. But as councils get more familiar with other solutions, I know here in Canterbury, there's been a lot of recessed windows details gone through council now, and they know what they're looking at. And that's really important, that as the people become more familiar with international best practice, then it will become more acceptable.
I think, sorry, we know that, E2 AS1, when it was made in response to, the leaky building crisis, keep water out of the building, prevent accumulation of it. So chuck the windows out as far as you can, so if they do leak, that there is drainage there. And admittedly, there was no recognition of thermal performance and that sort of thing. So I think as we go on into iterations of the building code and improvements, they're slowly starting to sort of try and meet all the clauses at once instead of just satisfying one and it being detrimental to something else. So massive thermal bridging with say cold aluminium, that's been sorted to a certain extent by thermally broken aluminium now, but the positioning of the window to be able to perform best thermally there's still no acceptable solution there. So I think we might be talking about windows soon, so I better shut up and let Soren talk.
Yeah, it's good.
I just want to say that Soren's going to go on to talk about the advances in technology now, and we're going to see what changes that does make.
Yeah, so we're about to jump into that, and I think one of the things that we've been talking about prior to the session was if councils push back on a detail which is a new detail and not E2 AS1, what we are really wanting to turn on its head with this is to ask the same question of something which is just E2 AS1. How does this window comply with H1 and how does it comply with E3? Describe that. And if a designer can't do that because those other code clauses are equally as important, then we need to look at the acceptance of new details that are clearly able to work. So that's what we're all about. We're trying to push forward and move away from E2 AS1. So thank you to the respondents on that. I did note too, I think there was 20% that never have, never will designed with E2 AS1 details. So that's quite interesting and nice. It would be nice to know what those details look like, and they will be from the Passive House Designers design guide or handbook. They'll be from the Super Home movement. They'll be from Stark Windows and Doors, and we're going to have a look at those in a moment. So thanks, guys. Soren, we'll hand back to you.
Thank you, John. So now we're moving around the envelope to our favorite topic, which is windows. Windows are changing so much at the moment. We finally moved beyond plain aluminium, but that's a thermal question, not so much E2. So what's wrong with the E2 part of an E2 AS1 installed window? The answer is not much from that E2 perspective. If the PEF rod shown as the white blob here, in combination with foam, is airtight, everyone's happy. It's mint. And do you hear any cynicism here? Of course. We're going to come back to this, but first, the amazing part of these windows is the internal gutter, which is there to collect condensation, which is an E3 internal moisture thing. This gutter drains from inside the building to outside through holes drilled through the frame for this purpose. Is this clever or crazy? We call it crazy, especially when there are better options available. So let's get into the importance of the air barrier connection, then come back to look at these better window options. These slides are from Joe Stebrick's presentation. They clearly demonstrate the need for the wind barrier line to be connected. Again, there's a code up there on the right that will take you to more information from him. The image on the left is showing the cross section of a cup tipped on its side. Rainwater can land in the cup, can bounce around and drain out happily, providing the opening on the left-hand side is large enough. Add wind pressure in the picture on the right. You might initially expect rain could be driven further into the cup, but this doesn't. Why is that? Well, it's because the wind pressure is moderated by the sealed nature of the base of the cup, as shown between the two black arrows. There is nowhere for the wind to go, so it can't drive water further in. This should be telling you the importance of sealed systems at the back of the cladding cavity. Wall underlays connected, base of wall, headed wall, we've covered these already. Now we add pressure moderation with a baffle. And this starts to look familiar, similar to what's happening at the window head, window sill, and within the window frame itself. Here we can see pressure moderation in action in a window frame. The red arrow indicates air pressure entering the frame. So external pressure equalizes with the space within the frame through the drain holes. This in turn minimizes the pressure differential across the window seal, which is doing all the work defending rain entry. Notice how this would not work without the internal seal, which takes all the wind pressure, but is not doing the waterproofing. Now back to a typical aluminium window, and it doesn't make any weather tightness difference if it's thermally broken or not. Plain one here is shown. The cavity pressure is balanced with the exterior. We know this works in terms of E2, but it's reliant on the air seal between the framed opening and the reveal, which in this case is PF rod and sealant. So it's reliant on the window being connected to the reveal in an airtight manner. So tape it, and tape the miters of the reveal as well. The weather resistive barrier is now continuous by design. You can see that red line traces that continually. What's our offer here? In terms of design, simple. It's very hard or impossible to quality control PF rod and foam. And what about durability? So we should back the seal up with a tape connection that I'll show you in a minute. Here is a more high performance detail with the tape air seal connecting the joinery to the weather resistive barrier. It also features an intelligent air barrier and a high performance stark welded UPVC window. We have the tape air seal solution tested to E2 VM2 up to 2.25 kPa. This was done by All Facade Services at Health and Building Surveyors Test Facility here in Miramar, and is covered also by an Oculus judgment. Please reach out to us if you'd like to discuss this testing further. Now we go into another poll question.
Oh, crikey. Already into another poll question. Okay, so this is our one that was a bit out of order. So we were supposed to hit that one about E2. Why would you still design with E2 if you knew that there were better things to do? And this one now, we're going to step back a tiny bit into a question about the dumbest thing. So in each of our sessions so far, we have asked this same question. What's the dumbest thing we're doing for this particular code clause? So what is the dumbest thing we do for weather tightness? As an industry, not you personally, of course. So is it untaped wall underlays, as Soren described earlier? Is it using expanding foam for the critical air seal around a window? Is it using something like a porous wall underlay, which may have questionable weather tightness? Or is it a design choice around no eaves? So if you'd like to fill in your answer on that, and I'll get the panelists back up on screen in a moment, and you guys can discuss that and anything else related to the windows if that's of use too, as we've just covered. All right, how are we doing on those answers? What have we got? Okay.
Interesting. I was going to say if there was a fifth one saying all of the above, that would have been a most popular one. So it's a reasonably even spread between them all.
I'm happy to see my personal favourite, no eaves, has got a good.
Why no eaves? Why no eaves?
Oh, and it's such a fashionable trend. Architects are designing houses with no eaves, but I can see the value of an eave, like I can see the value of an umbrella. Maybe it's the pom in me. I don't know. I walk gentlemanly with my umbrella, but I can see the value in an eave and deflecting that first rain.
Yeah.
We live in an area with high rainfall. We can't kid ourselves.
Yeah, but I'm going to stop you there.
Yeah.
Soren, I'll bring you into this. You've just presented a slide specifically on parapets and how to make them work. Parapet would suggest clearly no eaves. What's your take on that? Can we design to keep water out at parapets? And it's a bit of a lowball question. Can we do it?
We can. Yep. If you're getting the 4Ds right.
That's it. We can. It can be done.
You can, but I guess where possible, you know, have some deflection. So obviously you can't get much deflection at a parapet, but at an eave, you know, if you don't have to have an eaveless detail, then put an eave in there, and it's you know, it works for the life of the building.
Yeah, but you're 100% right, Ben. It's a compromised piece of architecture, and then if you start applying more compromises to it, like you really want a good clean aesthetic there, then you're not going to build out with fascias and create drippages for your top ventilation, etc. Then, you know, you start to really squeeze the effectiveness of some of those Ds, and becomes more problematic.
But you know, I'm also a victim of fashion, and it is one of those things that it's about a style. And I do acknowledge that there are some architects out there really, when they want a no eave and they design it and they make it very, very clever. Of course, the outcome it does work, and it is beautiful, but of course the cost that it adds, and we just got to make sure that if we're building at the other end of the spectrum financially, that we're not just mimicking something expensive, but doing it the cheap way at a great risk.
And interesting, about a third of the people said untaped wall underlays. I mean, that's not something that most people are familiar with. It is becoming more popular now. Obviously, we recommend that at Pro Clima, and other manufacturers of underlays do. And it actually just makes sense. I mean, we're putting an air barrier there. If we're just loose lapping underlays and not making it a continuous layer like a rigid layer is, then it's not actually an air barrier. It's a water shedding surface, you know, during construction, but not wind tight. So it's interesting to see, you know, a lot of people saying that, which is great to see some sort of people thinking about that answer.
Especially as we're encouraging more ventilation up the inside of the external cladding. So we might be going to a 45mm cavity with the extra opening that Soren showed there with his vermin strips. We're encouraging the drying up through that cavity, which means we're encouraging an airflow, which means we're essentially blowing air up that lap and straight into the insulation.
Okay, hey, guys, I'm going to interrupt you there, but I want to keep you on screen for a moment, because Ben, your comment there, kind of related to the parapet, kind of related to our previous discussion. There's been a question which has come up, which is going to nail this, or at least hopefully our answer might assist with this. So the question is, the ventilation at top of cladding cavity. We were taught at university that the reason for keeping the top of the cavity sealed was to keep the cavity pressurized, and that it would not allow easy entry of wind-driven, moisture-laden air. I presume this is now superseded by advice that additional air circulation is more beneficial than detrimental. Is that correct? And then there's a comment there about the discrepancy between the guidance, which is the E2 AS1 guidance, and a government agency being the MOE. So put that aside. Can we answer that? So what about that? Effectively, what we're saying is superseding older advice. Is there any comment that you want to make around that?
Yep, I think that's we're really looking at the weather resistive barrier is the back of the cup. The cup is still open, it still works. We're not talking about massively open. Sure, it is a maintenance water ingress risk with top ventilation, but it should still be vermin protected, still relatively baffled, but it allows another location where pressure equalization of that cavity can work.
So it's not a philosophical decision, it's a practical decision about where the air barrier, or maybe an easier way is to call it wind barrier. So where that wind barrier line is at the back of the cavity, that needs to be continuous. The bit at the front, the cladding, can't be, is very, very difficult to actually genuinely make continuous anyway. So what we're doing is saying when water gets in, drain it out and dry it out.
Yeah, I think the language around that is pressure moderation, not pressure equalization. The pressure in the cavity is going to be a little bit different from the outside and different from the inside, but it's sort of moderated, so it's not under negative pressure, like sucking moisture into that cavity and going through any little gap and crack, but moderated to allow, you know, free drainage down that cavity. Yes, it's going to get through, but it needs to be allowed to drain through, not jump across to layers and find gaps and get into our envelope. So,
and it's about durability. Can I bring in durability on the top there? Systems fail. The idea is that over time systems fail, and when they do fail, we need to make sure that we are allowing the drainage and drying. So if we do get water egress, which can happen, is that we're making sure that we're doing everything we can to dry it out as well.
All right, hey, we should probably keep moving. That's a good plan right now. So Soren, we're gonna jump out and hand back to you to carry on, and we'll see you again in a moment.
Cheers, Sean. So what about the roof? If your risk matrix is over 6, you're going to put your relatively low risk vertical wall cladding on a cavity. Yet we continue to direct fix our roof right down to 3 degrees depending on the profile. Here we see a direct fix corrugate on the right, where we have the corrugate on underlay, on purlins, and typically a 25mm gap to the insulation, which is should ideally be ventilated, but not always the case. Ventilation would wind wash the insulation. All the roof fixings are penetrating the underlay, and they're through the high point of the corrugate profile, so the underlay is able to move around the fixings, which is a durability issue. On the left is a European best practice above sheathing ventilation system, where we have a separation layer between the cladding and the exterior treated purlins. The counterbatten packs the purlin off the underlay, which is directly on top of the rafters. So the insulation fills the entire rafter depth, and in this case, it's in contact with the backside of that underlay. The roofing fixings do not penetrate the underlay, which is ideal for fitting solar array. The sky aerial guy can get up there and screw into the purlin only in future, and it allows a reclad whilst maintaining a continuous weather resistive barrier. The underlay is clamped between the rafter and the counterbatten at the fixing penetrations of the purlin screws, and these penetrations can easily be sealed with a butyl tape. The difference between these assemblies is chalk and cheese really, and you can guess which one will have less external moisture loading, which is something that Richard mentioned earlier. So which one's going to have the better drying ability and less moisture loading? Here we're looking up under a direct fix corrugate roof, and we can see the lines where the roofing iron is in contact with the underlay, cooling it and causing condensation to form below, which will in turn drip down into the insulation. The weather resistive barrier is not able to provide a good second layer of defense if it's able to wet behind it. Think about that. This sketch shows a skillion roof. It's from one of the latest Brands Build articles, actually 1st of April 2024, so it's brand new, called a skillion roof design. And there's a QR code there for that as well. Looking at 3 of the 4 Ds, the cladding deflects rain, the cavity has space to drain without ponding, and there is also dedicated drying pathway with opening at the eave and apex. What's interesting here are 2 additional things. Firstly, note the connection of the wall underlay up to the roof underlay. No wind movement is allowed to occur within the insulation, and this is both an insulation performance aspect and a weather tightness performance aspect. Secondly, there's a dedicated plywood air tightness line on the inside of the insulation. It's on the warm side there of the skillion roof, preventing moisture loading towards the roof underlay. Ministry of Education designs now require above sheathing ventilation. That means airflow below the cladding, but above the rafter in this image. MOE cold roof detail also requires a vapor check on the warm side, where you can see the plywood dedicated air tightness layer in this picture. And this is also the sketch that I pulled the top ventilated wall detail out of. We looked at that earlier. You can see that there. The final D of the 4 Ds, durability. What would that be? Pick a weather resistive barrier for your second layer of defense that has a really good UV resistance, remembering it could be re-exposed for a reclad. Pick one that can handle temperature stress, and pick one that's monolithic membrane, not microporous. You don't want it to wick moisture into the insulation. That brings us into the final poll question, John.
Great, good stuff. Thanks, Soren. So we're going to jump straight into this poll question because it's a goodie and that'll feed into our questions. So we've got a good number of questions coming through, some of them relatively straightforward, some of them good hard questions for us. So what we want to just quickly drill down into for the final stretch is what you as a designer have influence over and what you can improve. So the question is, what can you improve out of clause E2, solution E2 AS1, and the tested solution E2 VM2? So out of those three, there is actually only one right answer, just to speed this, and it doesn't matter whether you get it wrong, we're not criticizing, but there is only one that can be modified by you or improved upon by you. So let's close that poll because we really want to kick into some of these other questions too. Okay. So maybe it was a slightly loaded question or a tricky one to understand. So I'll take the credit for that. That was my question. But guys, do you want to jump in and discuss that? So let's go through them one by one, so that we can just make sure that we're understanding what these things are and how they can be used.
I guess firstly, 20% of people said E2. I guess technically, if you improve on anything underneath E2, you are improving E2. So that's a technicality. We'll give them that one. But the higher objectives of E2, you can't really get better than preventing accumulation of water and stopping stuff getting wet and moldy and decaying. So yeah, first one, you can't improve on E2 as a high level objective.
Unless there's people out there feel they'd like to rewrite E2.
Yeah.
But as it stands, as it stands, as a piece of legislation that says prevent accumulation of external moisture. That's if you do that, you've met the code. It's not sort of it is a black and white kind of approach with that. Okay, let's hit E2 AS1.
What was the?
It's only one solution, isn't it?
About half the people.
The E2 AS1, I was reading through it and looking at some of the pictures before we came on, just to sort of keep it fresh. And that's our job, I believe. I believe our job is to find better solutions at all times. When we invented the car, we didn't just stick with a Model T Ford. We improved and improved until we've got something that's quite reasonable.
Which Ben, so that's exactly what Soren has nailed, right, in this presentation. Just take the base of the wall. That detail that Soren showed was a base of wall detail showing a wall underlay coming down and just loose laid, just literally flapping in the breeze. And that is an E2 AS1 detail. And the improvement upon that is to seal that back to the slab, because you've then improved the wind tightness of the building envelope, but you have not changed the weather tightness, or actually you've improved the weather tightness, but you haven't degraded the weather tightness. You haven't provided something which is going to trap moisture, unless of course you flood your house, which I don't know. Is that something that we should be designing for, a full flood inside your house?
Well, that's an E3 problem, isn't it?
Sweep it under the skirting boards.
Okay, and then finally, what about the VM2? What about that? Can we improve upon somebody else's VM2 tested result?
I mean, it's an independently verified test. I mean, that, you know, it's a way of proving that your system works. So it is what it is, I guess.
You can't argue with the result, but you could maybe argue with the method and say, I'd like a better result. And so there's that opening there. You say, okay, yes, your E2 VM2, that's independently tested, and we like the outcome, but actually I've got a better idea. That's what we should be striving for and building all the time.
Exactly.
VM2,
So while
if that was a card,
this
that
getting back to
trumps
E2
the
AS1, sorry, just a lot of the stuff that we
VM2. Well, we've got 3 people talking, so
the internet problem
Soren,
there.
let's go you.
Yeah.
So if the VM2 was a card,
Okay.
does that trump
I'm handing
the
across to
4284
Soren.
and
Yes.
the VM7 test?
It does, because EM7 is a test method, which is, I mean, like all methods are made up, but that is not accepted or recognized in the same way that the VM2 test method is accepted. So verification method means independently verified to a particular, in our case with our tape, a particular wind pressure, wind and water. So is that answering your question, Soren? Is that enough?
Yes.
Probably. Okay.
Spot on.
Hey, we've got a few minutes left. I want to just transition into a related question to that. So, does a product need a brands appraisal or code mark certificate to comply with E2, or to be, maybe I'll rephrase that fraction, to be used in a building in a compliance with E2 approach? That's a little bit tricky. What are the alternatives? Richard, can I hand that across to you?
Yeah, sure. I mean, an appraisal or a certificate, I guess, is someone else saying, hey, this complies because of this, this, and this, and when this and this is done, you know, independent thing. It's great, and it's become, you know, brands appraisals especially have become sort of the go-to thing. Show us your brands appraisal, tick the box, you know, move on. But it's not the only way. A product doesn't need a brands appraisal. We've been talking about independent testing and testing to VM2 and this standard and different methods, like the air seal test with the tapes. You know, that's a proper laboratory doing a test to proper standards and showing that a tape can be used for an air seal as part of the weather resistant barrier around a window. That hasn't got an appraisal for that application, but that's a compliance, showing compliance to a standard and meeting the requirement of the code, which is, you know, prevent accumulation of moisture. So long story short, no, you don't need a brand appraisal or a code mark. There's other ways of meeting that.
Oh. Okay. Slightly tricky one. Roof noise of metal roofing worse. So let's call it rain noise on metal roof. I don't think anything that we've shown
Pinging, perhaps.
Should.
It'd be because of the separation ASV versus E2 AS1 I'm picking. Not having the roof underlay directly under the roof versus having having a cavity and then the underlay like we're showing, versus having the underlay directly under the roof, having that underlay potentially being able to absorb some noise. I think that's probably what the question was. But
what's the actual answer? Does it actually make the roof noise worse?
I don't know. There is more separation there. There's a vented air cavity below there, so there is actually, the roof is actually more separated from the envelope in that vented cavity detail versus the E2 AS1 method. So I wouldn't have thought so.
I think the mountain type of insulation is probably going to make more difference.
Yeah.
All right. Let's go to a question about the roof. Soren, are you able to go back to your slide, which is the image of from brands, just the last one on the roof? Okay. This question says, instead of bringing the wall underlay up directly under the roofing underlay, as shown, can it carry along the horizontal soffit and connect to the roofing coming down behind the fascia? So can we do, so up the wall, right hook out along the soffit and connect up there? Ben, shall I throw that one to you?
Thanks. Yeah, I love soffits. No, why would you? It's the roofing paper at the top is an umbrella. This is my opinion. You're deflecting water away from your wall, and you're trying to create a deflection there. Any condensation that's got, or the condensation that's formed in that cavity will run out away from your wall. I don't know why you'd want to run it out under your soffit and create a sort of a potential horizontal plane, which is going to accumulate. I wouldn't recommend it.
I have been involved in jobs before where there has been probably bigger commercial jobs with a different sort of build up to this, but where there's been the wall underlay used as part of sort of the wind tightness layer, I guess, to include that soffit area in the envelope. But as you know, as Ben was saying, as long as there's a piece of underlay above that to stop the accumulation of water pooling in that horizontal piece, there's some there's some things that you need to do to ensure that it wasn't creating a problem. Yeah.
Cool. Okay. Right. So I'm going to try and pack in two last little questions here. They're not too crazy. Well, they're weird questions. Here's the first weird one. If the top of the cavity is open, do you need a vermin barrier at the bottom? Is the drafty cavity not unattractive to vermin? Who wants to deal with that? Who wants to deal with the comfort and health of vermin?
Yep, so nice that we're constantly. That's great. Sorry, Soren, go.
Yeah, you will get stack effect, and you can get quite high cladding temperatures depending on your cladding type and color. So warm air and air movement is the perfect place that Mr. Spider is going to see, hey, let's just spin a web over this and trap any other critters that come along. So you will quite often see cobwebs and things. So you're going to be washing it. It is a maintenance water ingress risk area that you need to be very aware of when you're detailing. And yes, you do. It's a E2 acceptable solution requirement that you have that minimum vermin protection. I think it's a maximum of a 5 mil gap from memory in terms of that dimension of slot.
Yeah.
If it was Australia, you've got for these openings here, you've got bushfire considerations, so they have a much smaller orifice, and generally they're going to use a sort of a wire mesh or something like that. But yes, you definitely need any openings to be vermin protected, bottom and top.
Vermin might be similar to humans in that they like a sort of a nice ventilated, dry environment. So without having a vermin strip there, you might actually make it more attractive to vermin.
Good. All right. Thanks for that. Okay. We've got a question. It was actually the very first question. I just was hiding at the top here. Was can you show a sketch of the proposed parapet detail? So that's a great question. We can't answer directly here, but what we can do is make that available. Maybe we just need to point people toward our construction details, but I think it is a good question or good point. So Soren, what you had on screen was kind of like what is common, but not what an awesome solution might look like. So let's try and do that. Maybe we'll do a post or a blog or an article on EBOS that just unpacks that a little bit more for the future. So we are actually out of time. So in 2 weeks, we will be examining H1 energy efficiency and answering the question. Well, it's actually, this is our colleague, Catherine McGregor, who's presenting this, and she's going to talk about her own home. So the question that she's asking is, why is my 6-year-old house impossible to heat? And as we're finding out, some of the things that we've been doing as an industry just aren't that clever. We just don't need to be cold. I can't even read my own notes on this. We just don't need to be cold. She's in Arrowtown, and she's going to be presenting a comparison between Arrowtown and Auckland. Auckland's way better, of course. So I'd like to thank you all for attending, and also our panelists, Ben and Richard, and our presenter, Soren Webb. Please feel free to get hold of our team for in-house presentations and on-site assistance. Thanks heaps for attending. We'll catch you next time.